Hi everybody, this is section 8.7. This is log and exponential equations and applications. This is going to be sort of the longer section in this chapter, but it is the last one in this chapter. There's only one section to go after this, and that is from chapter 4. So this is the last section in chapter 8. So when we have an equation with a log in it, it's called a log equation. Essentially, there are a couple of particular steps that matter when we're solving log equations, and here they are. The first is to isolate the logs on one side. This is a big deal. From there, you're going to write all the logs together into the sum or difference of a single log. Your goal is to get it to be log of whatever equals something over here, okay? Logs on one side, all just in one setting, and then whatever's left on the other side. Rewrite, you want to take this equation once you get it and rewrite it in exponential form, and then you can solve it. Okay, you check this, you got to check the solutions to make sure they fit in the domain, but this is the idea. We're going to write it as a log, change it to exponential form, and then solve it. So in this case, there's only one log on one side. It's already in a form I can convert. So remember, we go from log base b of something equals y becomes base to the exponent equals the argument, okay? So in this case, 3 to the first equals 2x plus 5. Well, that's simple enough to solve, right? It's just a matter of rewriting it. I'm going to subtract 5 from both sides. I'm going to get negative 2 equals 2x divided by negative 2. X equals negative 1. That's how this goes. Okay, you can check the answer, make sure you can actually take the log of that, all is well. All right, so you try this one. If you set it up, you're going to set it up as 6 to the power of 2 equals 5x minus 4. You can solve that, right? That's not a huge deal. What happens is when there's logs on both sides, things get a little more complicated. So the first step is going to be to combine them all to one side. So I'm going to take this log base 4 of x minus 3 and move it over to the left. Make sure I have enough room. Okay, so on the left, I'm going to have log of x, log base 4 of x, and they have the same base, so I can combine them. Log base 4 of x plus 3 equals 1. So now I'm going to combine what's on the left into one log. Log base 4 of, when they're being added, that implies multiplication, so x times x plus 3 equals 1. Now I'm going to rewrite that in exponential form. Now I'm at the same spot again, so I'm going to have 4 to the first equals x times x plus 3. And now I just have to do the algebra to get me where I'm going. Distribute the x. So I have 4 equals x squared plus 3x. That's a quadratic, so I'm going to move that 4 over. I'm going to get 0 equals x squared plus 3x minus 4. Now I just have to factor it, which is something we've been doing for ages. Okay. It was a minus 3, wasn't it? This shouldn't have been a plus. Somehow along the way, I decided to make it a minus. I need the eraser. I can't get it to erase. Okay, fine. I'm trying to get it to erase. There it goes. That should be a minus. Okay, sorry, got my symbols a little backwards. All right, so we have minus minus. So now we're going to factor this. Let's see, multiply to 4, to negative 4, add to negative 3. That gives me x minus 4, x plus 1, right? So that means x is going to be equal to 4 and negative 1. When you go back and check, you have to see if it all works out. So I'm going to go in and check both answers. I have to check them on my original equation, which just helps if I can see. So I'm going to do the log base 4 of 4 equals negative 1 minus log base 4 of 4 minus 1. So log base 4 of 4 is going to be 1 equals 1 minus log base 4 of 3. Okay. So, or sorry, log base 4 of not 3. 4 minus 4. I turned my head for a second and got myself distracted. 4 minus 3. That's where it should be. Hold on. That should be a 1. So log base 4 of 1 just gets me 0. 1 minus 0. Oh, sorry. I'm looking at the wrong thing. Log base 4 of 1, that's going to equal 0. 1 minus 0 is 1. Okay, so that's going to work out. If I do the same for negative 1, I'm going to get log base 4 of negative 1 equals 1 minus log base 4 of negative 4. That is not going to work out. So in this case, negative 1 is not going to check. Okay, so one of my answers in this case is going to be all right. All right, you try this one. When you get all down to the end, you should be checking x should be 9 and x should be negative 1. If you go back and check, 9 is going to work, negative 1 is not. Okay, so please try them. The more you practice, the better off you will be. Remember, math is all about practice. How'd that get all the way down here? All right, so now let's try another one. This one looks just like the last one, doesn't it? Remember that when there's no base on the log, the implied base is 10. So I can rewrite this. All the logs are on one side, everything's fine. So this is 10 to the 3.7 equals x plus 300. Well, it's fancy because you have a calculator. You can do 10 to the 3.7. Okay, I'm actually just going to move that 300 over because I'm not going to do that right this second. So I'm going to do 10 to the 3.7 minus 300, and that equals x. You have a calculator, calculate that through. It should equal something in the neighborhood of 4,711.87. It's fine, okay? Oh, I got these all out of order. What happened? All right, this one works the same way. We just keep doing the same thing time and time again. When you get this one done, P should be somewhere in the neighborhood of 13.95. Try it. Okay, so there is another case of log equations. So in the first case, we can combine the logs on one side and we can change it to exponential form. That's the first way to do this. The second way to do this is if there are logs everywhere and there's nothing left if I move them all around, there's a rule to help me. So if I have log base b of x and log base b of y and they're equal, they're set equal, basically it implies that x equals y, right? Because these guys sort of drop away. So if I see logs of the same base on both sides on everybody, I can just drop them and they can go away. So in this case, I have ln of x plus 2 plus ln of x minus 1 equals ln of 9x minus 17. The goal here is to make one log on each side, and then you can drop them. So on this side, on the left, I'm going to do ln of x plus 2 times x minus 1, because when they're added, that's implying multiplication, right? And then over on the right, I'm going to have ln of 9x minus 17. Now I have my rule. These guys can drop away. Now I'm just going to solve it without the ln's, and life is good. So on this side, I'm going to have x squared minus x plus 2x minus 1 equals 9x minus 17. X squared plus x minus 1 equals 9x minus 17. I'm going to move everything to the left. And I'm going to get x squared minus 8x plus 16 equals 0. Well, that's factorable, isn't it? Plus 17 plus, that should have been a 2. 2. That's a 15. Okay. So then I get x minus, let's see, minus 3 and x minus 5. I was trying to add in my head instead of multiply. I'm going to get x equals 3 and 5. I can check them. Both in this case work, okay? This is the second process. So when everybody has a log, we're going to make one log on each side and then they drop. So do the same thing here, same idea. What you're going to get is combined on the left, ln of t minus 3 times t minus 1 equals ln of 2t minus 5. ln's drop away. Just solve it, okay? In this case, t is going to equal 2 and 4, but only one of them is going to work, the 4. The 2 is not, so please be careful to check them. All right. We can also solve exponential equations, okay? We can go the other direction. When we have an exponential equation, basically the first way to solve, so for logs we had two ways. We had log base b of x equals y, make exponential, okay? If we had log base b of x equals log base b of y, drop. Okay, so that's one, that's two. In exponential form, we have two choices as well, okay? So the first choice in exponential form is basically sort of the corollary to the second way of log. If I have b of x equals b of y, the base is the same. It implies that x equals y. So if I can make the bases be the same, I can just ignore the bases and use the exponents. But the trick is getting the bases the same. So this base is 4. So I have 4 to the 2x minus 9. Is there a way to rewrite 64 with a base of 4? Well, yeah, there is. I can write it as 4 to the third because 4 to the third is 64. Now the bases are the same. I can ignore them. So I can solve 2x minus 9 equals 3. Awesome. Plus 9, 2x equals 12, x equals 2, 6. Okay, please check it. It does check in this case. All works out. Okay, try this one. This one is 2 to the 3x plus 1. And then I need to say to myself, like, is there any way to rewrite 8 with a power of 2? Well, yeah, 2 to the third, right? So then I can solve 3x plus 1 equals 3. Not the big deal. All right, let's try this one. This one is a little more convoluted, right? But it doesn't make it any different. I can make 1/4 have a base of 2. It's just a matter of how I get there. If I think about 1/4 is really 2 squared, isn't it? And I want that in the numerator, so if I flip the sign, I make it 2 to the negative 2. That's the same as 1/4. So I'm going to rewrite this. 2 to the x times x plus 3 equals, 2 to the negative 2. Okay, well, now I can just distribute here. So I get x squared plus 3x equals negative 2. And you know how to do that from there. Okay, we've been factoring and factoring and factoring our little hearts out all semester here. All right, then solve. I get x, let's see, x plus 2, x plus 1. So that means x equals negative 2 and negative 1. Both of them work. If you check, you should, please check. Okay, try this one. So first I'm going to mess with my exponents here. I get 3 to the x squared minus 5x. And then I have to say, can I turn an 81 into a 1 over 81 into something with a base of 3? Well, yeah, I can. Because I can rewrite 81 as 3 to the 4th. And then I can get it in the numerator by writing 3 to the negative 4th. So that's just going to be 3 to the negative 4th. So now it's just going to be x squared minus 5x equals negative 4. Now we're just back to factoring. The answers here is going to be 4 and 1, and both check. All right. This one is where the last instance of solving an exponential equation comes in. Because here's the thing. It's great. The preferred version is make the bases the same, ignore the exponents. Happy day. But there are times when you can't make the bases the same. Okay, so this is method number 2. What you're going to do is take the log of both sides. This is if option number 1 doesn't work, okay? If I can't change them into the same base, and in this case I can't, there's no way to take a 25 and give it a base of 4 to a power and make 25 out of that. So here's how it works. I'm going to say log and log. So I'm going to get log of 4 to the x equals log of 25. Okay? What this allows me to do using my log rules is pull the x out of the exponent to the front. So I get x equals log of 4, or x times log of 4 equals log of 25. I'm just using the base of 10, which is fine. Now I can just divide by log of 4. In your calculator, you can do log 25 divided by log of 4. And that's what my answer is. So x in this case is just equal to whatever that division is. It's somewhere in the neighborhood of 2.322. You cannot survive this section without your calculator, so go get it if you haven't. Try another one. In this case, there isn't, I can look at like 32 is a power of 2, but it's certainly not a power of 5. So I'm really just going to take the log of both sides. Log of 5 to the x equals log of 32. That's going to let me write x times log of 5 equals third log of 32. And I'm just going to divide by the log of 5. Not terrible. So I get x equals something 2.153 or so. Okay. So the rules are written out right here. Okay. Isolate one of the exponential expressions, take the log of both sides. You can use the natural log or the common log, doesn't really matter. So but this is the way you do it. So you don't pick a base of 2 because you can't do that on your calculator. And use the power property to get exponents into multiplication rather than as factors. So let's try another one. This one is a little more complicated, right? So the first thing I want to do is isolate the exponential expression. So I want to get the part with the exponent alone. So I'm going to move 2 to the other side. So I'm going to get e to the negative 3.6x equals 7.74 plus 2. Okay, great. Well, now I know what 7.74 plus 2 is, so I'm going to do that. Combines like terms, 9.74. Now I'm in a pretty good spot, right? Now I can take the ln of both sides. It's useful here to use the natural log because I have an e. So ln of e is actually just something that cancels. So this becomes negative 3.6x. ln of e is 1, so that just leave it be. That just, and this comes to the front, so it just stays where it was. Equals ln of 9.74. Okay, so now I'm just going to divide by negative 3.6. And you get an x. Okay, x is going to be negative 0.632. Okay, got to try these. You have to practice this. Okay, so this one works the same way. Try it. T should get you somewhere in the neighborhood of negative 10.0878. All right, let's try a different one. This one has exponents on both sides. That is okay. All right, so I have exponents on both sides. I'm going to just start by taking a log or an ln. I'm going to use ln in this case because why not? 2 to the x plus 3 equals ln 7 to the x. I'm going to pull the exponents out to the front. So x plus 3 ln of 2 equals x ln of 7. Now it's a little funky, right? Well, what I can do right now is I'm going to distribute this. Okay, so I'm going to get the ln, x times the ln of 2 plus 3 times the ln of 2 equals x times the ln of 7. Sounds like a strange thing to do, but bear with me. Then what I'm going to do is move the ln's with the x's all to one side. So I'm going to move this guy. Actually, I'll move. It would be smarter to move the other one, right? So I'm going to move this guy over to the other side. Okay. I'm going to give myself some room. So on the left, I'm going to have 3 ln 2. On the right, I'm going to have x ln of 7 minus x ln of 2. I can write that now as the product of 1 ln. I can factor out sort of the x, basically, not the product of 1 log. I want to factor out the x. So pull the x out. That's going to be ln of 7 minus ln of 2. Now I've isolated my variable, right? That's what I wanted all along. Now I can just divide by this. So I would just do 3 ln of 2 times 3 times the ln of 2 divided by the ln of 7 minus the ln of 2. And if you need to figure them out on your calculator and write what that is and what that is and what that is and calculate them, do that. When you get all is said and done here, I get somewhere in the neighborhood of x equals 1.66. Okay? It sounds complicated. Take your way through the steps. Do it a couple of times. Okay? Practice it. There's no substitute for practice in math. So let's do this one the same way. So I'm going to take the ln of both sides, 3 to the x. I can take the log 2, same difference. 8 times x plus 2. We're going to do the same thing. I'm going to pull the x to the front. X times ln of 3 equals x plus 2 ln of 8. I'm going to distribute here. So I get x ln of 3 equals x ln of 8 plus 2 ln of 8. Now I'm going to group the ones with the variables. So I'm going to move the x over. So I get x ln of 3. I keep writing that as one word. Minus x ln of 8 equals 2 ln of 8. Factor out the x. So I get x ln 3 minus ln 8 equals 2 ln 8. And divide. Ln of 3 minus ln of 8 equals, divide. And then it's just calculator work. Okay, so in this case, x is going to be somewhere in the neighborhood of negative 4.23. Okay. Now we're going to get to some application kinds of things, and this is basically almost the end. Okay. So the population of the world was estimated to have 6.5 billion people in April of 2006. The growth rate is 1.4%, and it's defined by this population function. Okay, it represents population in billions. So you want to estimate 0 years is t at April 2006. We want to estimate the population 4 years later, so 2010. So what we're going to do is we're going to use 4 years later, because that's the difference in the time. 6.5 times 1.014 to the power of 4. That's just calculate. So put it in your calculator and calculate yourself an answer. The answer you get is somewhere in the neighborhood of 6.87. 6.87 what is the question? Well, 6.87 billion people. Okay. Oh, I should plug in my computer before it dies on me. Okay. All right. Now we're going to move to the second question. Same setup. Use the function to estimate the amount of time it would take to get to 13 billion people. So we're just going to set this up a little differently. So now we're trying to figure out t rather than the population. So I'm going to set this up as 13, because that's the population in billions, equals 6.5 times 1.014 to the t. Well, I can move this to the other side, right? I can not have to deal with that. So 13 divided by 6.5 is 2. I get 1.014 to the power of t. I don't know how to make those bases the same, but I can take the log of both sides. Log of 2 equals log of 1.014 to the power of t. Move the t to the front. Log of 2 equals t log of 1.014. Now divide away the log of 1.014 to both sides. So log of 2 divided by log of 0.014 equals the amount of time. That is going to be somewhere in the neighborhood of 50 years. So it's going to take around 50 years. That's going to be somewhere around 2056. We're going to get 13 billion people. Okay. You try these. The world used the same functions. For number 10, it should be somewhere around the neighborhood of 7.9 billion people. And for 11, it should take somewhere around 23 years. All right? All right, one more. The half-life of radioactive iodine is 8.4 days, 8.04 days. If 10 grams is initially present, the amount still present after T days is given by this formula. Use the model to approximate the amount still present after 2 weeks. Okay, round to the nearest tenth of a gram. So I want to find the amount. I'm given T. T is 2 weeks, but it says in the formula that it's in days, so 14 days. So I'm just going to calculate. A of 14 equals 10 times e to the negative 0.0862 times 14. Use your calculator, friends. When you do this, you should get somewhere around 3. And this is an amount, so we're talking in grams. Okay. We're going to now, same formula, it says how long will it take for the amount to decay to half a gram, round to the nearest tenth of a day. So instead of finding the amount, we're finding the time. So I'm going to put 0.5 as the amount equals 10 e to the negative 0.0862 t. Well, I'm going to get rid of the 10 first. I can divide by 10. So that's going to get me 0.05 equals e to the negative 0.0862 t. Well, now I can just take the ln of both sides. I keep trying to extend the page without exactly extending it. So I'm going to do ln 0.05 equals ln of e to the negative 0.0862 t. ln of e cancels. That's a 1. So it's just going to bring that to no longer be an exponent. Equals negative 0.0862 t. Now I just have to divide by negative 0.0862 to both sides. And I'm good. T should get you something in the neighborhood of 34.8, and that's in days because it's time. Okay, that is the end of 8.7. Good job sticking with it. Keep practicing. Ask if you have questions. I'll see you in the discussion.